In the previous video, we looked at how to measure the variance or the variation in a variable. Okay, so this time what we want to do is to take a look at the variation in the outcome variable and account for this variation. In other words, explain the variation in terms of variation in other variables. Okay, so we measure the variance in the variation or variance of the response variable, and then we try to explain or account for the variation in the response variable. In other words, our response variable may be height, and we see a lot of different heights, and we want to say, okay, why are these heights different? And we want to explain the difference in heights based on difference in some other variables. So that's what we mean by explain or account for variation in the response variable. And then, of course, having found out how much of variable we are able to explain, we measure what variation remains unaccounted for or unexplained. Okay, so once again, we go to our Galton data set. We look at the variation in the heights, which is our response variable, and we see that the total variation in the heights is 12.8373. So we calculated the variance of the column. Okay, now let's consider a model with no explanatory variable. Okay, which means what? That we are not considering any other variables as explanatory variables for the response variable, and therefore we can only say that the predicted value for the response variable is the average value. Okay, because there is no other variable, so we have no basis to say why there is variation in the heights. We can only say, well, the model value is the average height, which is 66.76. In other words, if I say I selected a person at random from this set, can you tell me their height? The best we can do is to guess the average height. Okay, so no matter which person you select, the model value is always 66.76, which is the average. Okay, so therefore there is no variability in the model value, and the model basically says, look, every person should have the same model value. So we are seeing variability, but the model says, well, according to me, everybody should have the same value. Okay, so the model is not explaining any of the variability in the height. Okay, so when you have a model with no explanatory variables, then obviously the model doesn't explain any variation. Okay, so that's what this is. This time we're taking the Galton data, calculating the variation, and the variance is of course 12.8373, as we've already seen. So what we're really saying is there a pattern in the variation of heights? So we could consider some other explanatory variables as explaining this. In other words, we can say, well, are people of different sexes prone to different heights? Okay, we know of course that males are generally slightly taller than females. Okay, so in our population there are males and there are females. So obviously we are going to see people with different heights, right? So some of the variation in heights is because there is a variation in the gender of the people. Okay, so that's what I'm saying here. In our data, we see people of different sexes. Okay, and we know that there is a relationship between the sex and the height. So obviously, it's no wonder that the heights are also varying. Okay, so this model, that gender is related to height, might explain or account for some of the variation in the children's heights. Not all, right? After all, if we said only the gender is accounting for variation in heights, right, then we'll have one model value for females, one model value for males. There should be only two different model values of height. In reality, there are many different values. Okay, so although sex accounts for some of the variation, it doesn't account for all of the variation. Okay, so what we are trying to do here is to find the average of the height by sex. So we find that in our data set, males have an average height of 69.223, females have an average height of 64.11. So our model value for males is 69.23 and that for females is 64.11. Okay, that's the model value. Okay, so now we've got the model value. If the person is a female, use the average female height of 64.11. If the person is a male, use the average male height of 69.23. Okay, so our model value will be determined based solely on the gender of a person. Okay, so now there is some variability in the model value. At least there are two different values. Okay, so here is our original data set. This is an excerpt, and to that excerpt we add the model value. So notice that this person is a male, so we put the average male height. Okay, that person is a female, we put the average female height, and so on and so on. Okay, so there is some variability now in the model value. Okay, and so let's do one thing. Let's add that model value as a column to our data set. Right, so we say Galton mutate. Remember, the function mutate is what we use to add a column. So now we say mutate mod val being standing for model value, equals mean of height, and we say dot by equals sex. Okay, in other words, if the person is a male, then mod val will have a value which is the mean height of males. If the person is a female, then mod val will have the value which is the mean height of females. So this is what happens. To our data set, we have added a new column called mod val, which is the male height if the person is a male, female height if the person is a female. Okay, so now what we are trying to do is to compute the variance of the response variable height and the variance in the model value. Okay, so we see that our response variable has a variance of 12.84 and our model values have a variance of 6.55. Okay, so we are saying, well, given that there is a value, there is variance in the model value, okay, so somewhat close to about half of the variance in height is accounted for by the variance in the model value. That's what we are saying. Okay, so because people differ in sex, we can expect a variance of about 6.55 in the height. Okay, however, the variance in the height is even more than that. It's 12.84. Okay, so we are saying here that the model explains about 51% of the variance in height. 51% means 6.55 divided by 12.84. Okay, so the sex or the model accounts for about half of the variance in the heights. The other half is not explained. We probably have to bring in other variables to explain that. Okay, so now let's see here. To our data frame, we are adding the model value just like before. Mod val is mean of height. And then we are adding another column called the residual. Residual is simply the response variable value height minus the model value. Okay, in other words, we are saying, well, model value is the model's prediction for a particular person, predicted height by the model, whereas height is the actual height. Okay, so the difference, height minus mod val, is what the model is not able to explain. Okay, so you could say that is the residual over and above whatever the model is predicting. And now we see the variance of the height, which is the response variable, the model value, and the residual. Okay, so we see the variation or variance of the residual is 6.288. Okay, and the important thing we see here is that the variance of the response variable is equal to the variance of the model values plus the variance of the residuals. This is always the case, and in fact this holds only when we calculate the variance by squaring the difference between the values. Remember, when we calculated the variance, we found the deviation, the difference between the 2 points, we squared it and then did the average and took divided by 2. The reason for that is so that this equation will hold, that the variance of the response variable is always equal to the variance of the model values plus the variance of the residuals. Okay, so this, of course, as we have said, the variance of the model values, that is what is accounted for by the model. Any difference, this is the variance in the response variable which is not accounted for by the model, unaccounted variance. Okay, so let's take a look at the numerical explanatory value. So when we had a categorical explanatory variable, okay, we said that the model value is simply the mean of the response value for each category. So for example, when we had a model where we wanted to explain the change in heights based on the gender or sex, well, the model value for males was the average height for males, and the model value for female was the average height for females. That is how we computed it for a categorical explanatory variable. Okay. However, if our explanatory variable is numeric, what do we do? Okay. In this case, what we do is we find the model as a line, the best line that goes through these points, the line that is closest to these points. And then once we have that, we can use that line to determine the model value. Okay, so plug in, suppose this is the mother's height is the explanatory variable and the child's height is the response variable. So what this model is telling us is, well, the taller the mother is, the taller the child will be. Okay, again, we are looking at a line model, we are not looking at a band model here. So now we can plug in the value and predict. So for a height of 62 inches, a mother with a height of 62 inches, we can expect the child will have this height. Okay, 66 inches height. Okay, that's what the model tells us. Okay, now let's see how much mother's height is able to explain the child's height. It will explain a little bit of the child's height, right? Because we saw that there is a pattern in the data. Okay, so this time what we're going to do is we're going to calculate the model values by using the model values function. Okay, earlier we just computed the average and we used that as the model value. This time we say, well, use the model height on, y equals f of x, height as a function of mother, or height as the response variable and mother's height as the explanatory variable. That will be the model value, which will be determined based on the line, right? It will plot the line, and for any given value of a mother's height, we can plug that in and get the child's height. Okay, and residual, of course, is the actual value minus the model value. And then again, we calculate the variances of the three. Okay, so notice here that the model value is explaining a little bit of the variation in heights. Okay, that is because even though the line that we had showed a trend, we still saw that the points were widely distributed above and below the line. Okay, so the line is explaining only a little bit of the variation. The model is explaining only a little bit of the variation in the response variable. A lot of the variation remains unexplained. The 12.32 of the variation in the height remains unexplained. The model doesn't account for that much. The model only accounts for 0.52 out of the 12.84. Okay. Now, of course, we could consider multiple explanatory variables, right? So first we could say height tilde 1 is the model with no explanatory variables. Height tilde sex is a model with sex as the explanatory variable. But we could have multiple explanatory variables. So we could have, for example, height explained by sex as well as mother's height. Okay, or even height explained by sex plus mother's weight plus father's weight. Okay, so the model is going to get more and more sophisticated, and of course, as we keep adding more explanatory variables, that will explain more and more of the variability in the response variable. Okay, of course, there are many other models possible. For example, height explained as a function of mother's height, height explained as a function of father's height, height explained as a function of mother's height plus father's height, etc., etc. There are many other possible combinations. Okay, these are all some possible models that we could consider. Okay, so first let's look at the model with no explanatory variable. Right, so this time we say Galton mutate model values height tilde 1. That is, build the model with no explanatory variable and determine the model value for every row of our data set. Okay, so this is going to, obviously the model value is going to be fixed, because we know that if there is no explanatory variable, then the model value is just the average. So the average is what is going to go into mod val, and then we calculate the residual and then calculate this. So obviously, since the model value is fixed, it's just the average, it doesn't explain, it has no variability. Okay, so this model of height with no explanatory variable obviously doesn't explain any of the variation in the height. So the variation of the residuals is exactly the same as the variation of the response. Okay, model doesn't account for anything. Okay, now in modeling, we are interested in this number called R square, okay, which is the proportion of variability in the response variable accounted for by the model. And we will now look at the R square for various models that we build. In this case, of course, R square is 0 because the model doesn't explain any of the variability in the response variable. Okay, let's consider one response variable, namely sex. Okay, so once again, we add the model values, which is a function, which will do all the work. We don't need to worry about doing the underlying work. Height tilde sex. Okay, we already know that in this case, the model value will be, if the sex is male, average height of males. If the sex is female, average height of females. So it's going to do all that computation. It knows how to do that. So you put it in mod value, and then we look at residuals, and then we compute the three variances. Okay, so this time we see, of course, that the model is able to explain roughly 50% of the variation in the response variable. Okay, so the R square is actually 51% or 0.51. So 49% of the variation remains unexplained. Okay, so that's the R square, which is nothing but the proportion of variability that is explained by the model. Okay, and we already know that for each of these, the model value is nothing but the average for the corresponding gender. Let's consider two explanatory variables this time, sex plus mother's height. Okay, so again we just say model values height tilde sex plus mother. Okay, so this time we see, since sex accounted for about 50% of the variation, we add mother and it went up to a little bit above. Earlier it was 6 point something, now it is 7.21. Okay, so now we see that the R square is about 0.56. Okay, that is because 7.21 divided by 12.84 is about 0.56. Okay, so this time the model is explaining a little more than before because we added one more explanatory variable. Okay, So this line, the general line, here I've drawn two separate lines for males and females. Okay, but we see that it explains much of the some of the more than half of the variation. Now we consider three explanatory variables, right? Father's height, mother's height, as well as the sex. Okay, so that's what model values: height, tilde, sex plus mother plus father. Okay, now we find that it explains a little bit more. It went from 7 to 8 something. Okay, and the R square has also gone up now to 64 or 0.64, 64%. Okay, so should we look for the highest R square? Not necessarily. Okay, we don't necessarily choose the model with the largest R square, and we'll talk more about this later in the course.